Suppose our mixture is composed of 50% butane and 50% pentane, and we want to obtain a pure butane product. Butane boils at a lower temperature than pentane, so if we heat the mixture to, say, 185 degrees Fahrenheit, more butane will be vaporized, and the condensed vapors will form a liquid that's enriched in the light component, butane. We can further purify this liquid by placing it in a second still and heating it at a slightly lower temperature. At 172 degrees Fahrenheit, for example, the condensed vapors form a liquid that contains 75% butane and only 25% pentane. This is because pentane has a higher boiling point temperature than butane, so less pentane vaporizes at lower temperatures. If we continue passing the liquid mixture through a series of stills that operate at lower and lower temperatures, we can eventually isolate a fraction that contains mostly butane. Because each still operates at a lower temperature, less pentane is vaporized as we move from one still to the next. Let's reverse the operation now and consider what happens to the liquid in the stills when we increase temperatures instead of decreasing them. At 185 degrees Fahrenheit, we said that more butane is vaporized than pentane. So the liquid that remains after the mixture is heated is enriched in the heavy component, pentane. If we place this mixture in a second still and heat it to, say, 196 degrees Fahrenheit, even more of the butane will boil off than did at 185. This changes the composition of the liquid to 75% pentane and only 25% butane. By passing this mixture through additional stills that operate at higher and higher temperatures, we can eventually form a pure pentane fraction. Because each still operates at a higher temperature, more of the light component, butane, is boiled off in each successive vessel. A distillation column operates on a similar principle as a series of stills, except that the entire process takes place in a single vessel.